The following is from Summer 2009 Math 263 Test 3, number 4. Consider solid bounded by z equals to x squared plus y squared and z squared equals to x squared plus y squared. I hope you see the difference. The first one without squared, the second one with squared. Now, notice that the right hand side there can be considered in terms of r. Okay, which implies this is z equals to r, provided that the r has to be positive. Now, if we want to find the intersection of the surfaces and we want to sketch the solid, we can see it this way: z equals to r squared, but also z equals to r. That way we see that r squared equals to r equals to 0. R squared minus r equals 0, then I factorize the r equals 0 or r equals to 1, right? Okay, now that's the intersection of the surfaces. So we will see that if we project the intersection on the xy plane later on, it will be a circle with radius 1 or the circle, the origin. Okay, but that's if you project that on the xy plane. Now let's try to sketch the solid. I wonder if this will work better. I will start with looking at the, let's say this is my r and this is my z. Okay, this is my technique of graphing it. Now first, z equals to r squared, that's basically a parabola. They will give me a parabola, but I will graph only the one on the first quadrant. And then the z equals to r, that's diagonal line. Okay, so this is my z equals to r squared, and this one is my z equals to r. Now you may wonder, Thomas, why do you want to do this in 2 dimension only, and basically why you do it this way? Now this is the thing, just to remind you how those things being done. Think about this way: if you have this is y and this is x, and you have, let's say, this is my y equals to x, right? Now when I replace the y becomes r, the y becomes z, and the x becomes r. Okay, that's basically, now it becomes, this is my r here, and this is my z here, right? But this has some kind of like 3-dimensional nuance in there. And what happened is, this means I will revolve this around the z-axis, okay, and that r now translate into, this is the y and this is the x. Okay, so it is actually now a cone. Okay, that's the idea. Now let's try another one. This thing here, the r and z equals to r squared, right? Now in 3-dimensional sense, this later on becomes x and this later on becomes y. I revolve this around the z-axis. That's actually a paraboloid, right? Okay, now if we look back here, what I will do is, then I will make this into 3 dimension now. Maybe I put it this way. Okay, this will then becomes my x, this later on becomes my y, this stay my z, but I will revolve this graph with respect to the z-axis. Now I don't think I can do it that nice here. It's all not nice anymore. Okay, but I hope you can see that the upper bound now is the cone and the lower bound now is the paraboloid. Okay, now that's the sketch of the solid. Now let's see what is the volume of the solid. The volume of the solid actually will be built on with that domain. Okay, the volume equals to double integral of that domain D. Let's call that domain D. Okay, and the upper bound is the cone, which is that one, right? Let me make it in sense of r minus the lower bound is r squared dA. Okay, and that's equals to integral from 0 to 2 pi, integral from 0 to 1, right? And then this is r minus r squared for r dr d theta, and because of the angle, the integrand and the limit of integrations are independent of theta, then I can take this 2 pi minus 0 out. Integral from 0 to 1 r squared minus r cubed dr, and I integrate that 1/3 r cubed minus 1/4 r to the 4th from 0 to 1. That's 2 pi times basically 1/3 minus 1/4. You will see that's actually 1/12, which give me pi over 6. Okay, now how about the surface area of the solid? Now let's see the top one. The surface area of the solid is equals to the surface area of the top plus the surface area of the bottom. Okay, now the surface area on the top, remember that's a cone, the lateral area of the cone, and we know that's equals to pi r L, where this L is actually the length of the slanted. And the r here, that's the radius of the base. Okay, now you can see the length of the slanted here. If this is 1 and that's 1, then it must be radical 2, right? The L will be radical 2. This is pi, the R is 1, the L is radical 2. You get radical 2 pi. Okay, now of course you can also do it using a traditional way. The following, let me do it here on a separate sheet of papers. Surface area of the top can be done as the following: z equals to the square root of x squared plus y squared, right? So z sub x equals to x over square root of x squared plus y squared. Likewise, by symmetry, c sub y will be the same, similar, I mean. Okay, such that c sub x squared plus c sub y squared plus 1 equals to x squared over x squared plus y squared plus y squared over x squared plus y squared plus 1, that is equals to 2, right? So the double integral, the surface area of the top, will be given by double integral of the domain square root of 2 dA, but that's actually square root of 2 times the area of the D of the domain, which is pi r squared. Okay, so even if you do it traditional way, you will still get the one we need. However, I do expect you to know some geometry, therefore you don't need to work that hard. Now how about the area at the bottom? the surface area of the paraboloid. Now z equals to x squared plus y squared. Therefore z sub x is 2x, z sub y is 2y, c sub x squared plus c sub y squared plus 1 will be equal to 4x squared plus 4y squared plus 1. Okay, now then the surface area of the bottom will be given by double integral of the domain square root of 4x squared plus 4y squared plus 1 dA. Now if I change it into polar, this integral from 0 to 2 pi, integral from 0 to 1, square root of 4r squared plus 1 r dr d theta. And with the argument of independence of theta in the inner integral and the integrand, then I can take the 2 pi out. Okay, and then I use substitution for, let's say, u equals to 4r squared plus 1, so du equals to 8r dr. Let me move it below. And this is in 2 pi integral what's that, u to the power of 1/2, and then du over 8 from 1 to 5. Okay, and that's equal to pi over 4 times the integral of u to the 1/2 is 2/3, u to the power of 3/2 from 1 to 5, that's pi over 3, 5 radical 5 minus 1. Okay, now then the total surface area equals to, so we look back there, the total surface area will be radical 2 pi plus pi over 3 5 radical 5 minus 1. Now this is from summer 2009 math 263 test 3 number 4.